Hello, my name is Zhong, and this is my Physics 2211 Lab 1 report on constant velocity. So this presentation can really be broken down into 4 segments, the first of which is the introduction, where I'll discuss the purpose and fundamentals of this lab. Second, the procedure, where I'll explain the experimental setup and results. Third, the code, where I'll share the code that I derived from the starter, and also share my experimental versus computational models. And then fourth, I'll answer the questions of what if and what does it mean. So the purpose of this experiment is to compare the observed position of an object traveling at constant velocity and the predicted position of that object based on a computational model. The overarching purpose of this experiment is to exemplify certain physics fundamentals, particularly Newton's second law. So here I have Newton's second law written out. F net is equal to the change in momentum over the change in time. Using some algebra and the definition of momentum, which is mass times velocity, you can find the velocity update formula down here. And based on the velocity update formula, a net force of 0 would yield a final velocity that is the same as the initial velocity. And that's important to really understanding how constant velocity is achieved here. So to set up my experiment, I first measured the length of the surface being used for the experiment, which is just a table in my dorm room. Secondly, I recorded a video of the duct tape, which is the object that I used to represent constant velocity. That duct tape rolling at a constant velocity across the surface. And then I inputted this video to the tracker application to determine the position of the tape from tame to frame. And then I used the measured positions to find initial velocity, and then used that to help create a computational model of the ball's position over time in GlowScript. Fifth, I compared the computationally predicted model and the tracker collected models through one graph. And then a little bit of a spoiler alert, I then determined the sources of error that caused the experimentally determined velocity to not be constant. So here I just have a video showing like how the experiment was set up, and the little red diamonds that I'll show up after I push this duct tape is just like measuring the x displacement from frame to frame. Each number is like a frame. This graph on the top right here, if you can see, it looks pretty linear, detailing displacement over time, but we wouldn't actually be able to tell if it's linear unless we really put it next to like a proven linear graph. All right, using the data from Tracker, I then found the total time elapsed from when I first pushed the tape to when it stopped, and that is just found by final time minus initial time at equal to 1.134 seconds. Then I found the initial velocity by taking the displacement of the tape from the second frame minus the first frame, and then second frame time minus the first frame time to find initial velocity using displacement over time, and that was 0.817 meters per second. Then I inputted all these data that I found off of GlowScript and the numbers I calculated for into GlowScript, and I changed the ball initial condition because it started out at 0.007826 meters in Tracker, and then the velocity I inputted in the initial velocity I just calculated for. Delta T here is equal to the amount of seconds that occur per frame, and in this case it's a frame per 0.033 seconds. Then I changed time to 1.134 seconds because that's how long it's rolled for. And then I changed net force to 0 because ideally we're working with 0 net force. I changed ball velocity to equal to the velocity update equation, and then ball position to be equal to velocity times delta t. So here we have a graph showing position over time for the experimentally determined one, and then the computationally determined one. And as you can see, the computationally determined one is perfectly linear since there is no net force. But the experimentally determined one, it like sticks close to the linear line for like maybe a fifth of a second, and then it deviates off, and because there's obviously a net force working on it to change the velocity. So most likely the frictional resistance between the tape and the surface, as well as the air resistance from outside the system, is causing this change in velocity. There are other things like tracking errors. Maybe I didn't put the tracker right in the same spot on the tape every time, or the imperfect alignment. Even though I aligned the axes to be pretty much aligned so it would only move in one dimension, there was likely still some deviation across 2 dimensions, which may have caused certain velocity decreases that wouldn't have been there if it only moved in 1 dimension. So to detail some of the further questions, what if the axes, if the positive x and negative x were interchanged. If this happened, then the displacement over time graph would simply be negative sloping with the same magnitude as before. But either way, for the experimental trial, the velocity would have approached 0 because of the net force working on it. And assuming net force is 0, is it possible for you to say how many pushes and pulls are added together? No, it's not possible because there's literally like an infinite amount of forces acting on the system, exerting a gravitational force on the duct tape, and therefore it's not like possible to account for and add up all those forces. But that's really all I have, so thank you.